Michele, and thank you. It is a great pleasure to be here. Actually, it's a place I really enjoy a lot. And okay, now we have to get rid of this, but I don't have.
You just say.
No, the thing is that I don't have my cursor somewhere. So yeah, exactly. Let's do something like this. Wait a second.
Fai exit, ESC, and then.
Maybe because.
ESC non funziona?
No.
Just ESC?
No,
No?
funziona. Siamo bloccati.
Fai got.
Got it, niente.
Niente.
Dopo.
Maybe exit the full screen.
Ok.
Ok.
Questo qui.
Okay, here we are. Ci siamo. As I said, yes, I was the first cancelled talk in Bologna, so I guess that's a kind of a distinction. To be the first one cancelled. So it's a pleasure to be back here, actually, to tell you a bit about what I was going to tell you that time, almost 2 years, more than 2.5 years ago. And the title, although it's called Understanding the Universe, I don't pretend by any means that I understand the universe, but I'm trying to just give you some ideas, some thoughts of the kind of things we are doing about the status of how to try to understand the universe. And our approach is going to be this model-independent approach that I will try to motivate in a bit. So the situation in cosmology is as follows. 6 parameters describe every observation in the sky, with some exceptions that I'm going to discuss in a bit. But now basically, I can just run my model over those 6 parameters and I can actually describe everything. However, what the energy densities are, what is the physics behind that, we don't know. What is the inflaton characterized by the amplitude and the tilt at the scale dependence, the NS, we do not know. Even to make baryons in a universe is very, very difficult because you have to violate the particle-antiparticle symmetry. So basically what you end up making is just photons. So most of the energy components in the universe, we do not know what they are. We do not know what the early universe was made of. So certainly description is not the same as understanding. And what I think I'm going to motivate is that we move beyond description and we go into the understanding phase. Now I'm going to make some remarks about how we are going to achieve this. And I think this is going to be appropriate to try to tackle the problem. It must be obvious to everybody that astronomy and cosmology is special because we cannot make any experiments, right? We are only observers. So the data are given, that's it. You can observe it, but you cannot touch them. And this is important because automatically that means that you have to be a Bayesian if you want to infer anything about the universe. And if you are a Bayesian with that trivial formula, it's just a product of the probabilities, you always have to check a model versus the observations. That's what you do. Now, when you do that, you have to put a prior into your likelihood to compute the posterior. Now, the prior is something that you choose. When you do parameter inference, it's very easy to eventually overcome the prior because your data becomes so good that at the end of the day, the prior doesn't matter. I can put a prior that I am now speaking from Kuala Lumpur, but eventually you collect data about my position from GPS, it's going to be obvious that I'm not there, but I'm here in Bologna, right? That's very good. So more data are going to tell us more about that. Although remember, we observe the sky, data are limited. But there is something that it is more catastrophic than that. And it is that you say, okay, very good. So I have all these different models of the universe. I want to choose them. How do you do that? Well, you have to compute the Bayesian evidence, which is the second line there. When you do that, the prior is always there. and there's no way you can overcome the prior. You can invent whatever prior you like, it will stay there. You can just put the delta function 1 over the model you prefer, and then no data will ever overcome the prior. So you have here a problem to be faced in the future about how do you choose the prior when you do model selection. So let me give you a very simple example, which is this one. I try to compute the evidence. The dashed line are my data. This is a toy example in 1D. And I choose 3 different priors: green, blue, and red, right? So most of you will say that red is the appropriate prior because, you know, it's not too complex. It is not too simple. But why? You need to have some kind of reasoning to decide what the prior is. Let me give you an example of actually data from cosmology where the prior is crucial. So you may ask yourself, I want to use cosmology to determine the hierarchy of the neutrinos. That is, if they are ordered normally or inverted. That is, basically, how do you put the 2 heavy ones and 1 light ones, or 1 heavy one and 2 light ones. This is very important in physics because it's giving you clues about how neutrino masses are generated, and even beyond that, can give you that later. Now, one thing that we have been pursuing is that actually you want to do this properly, you need to generate priors that are physically motivated. Because you have no other means of actually deciding which prior you are going to choose. And here there are some results that we publish in these papers where you actually use physics, for example, symmetry, and you say, well, all the masses of the 3 neutrinos are generated equally. There is no preferred mechanism for one mass or the other. Then there is already very strong, decisive evidence that the hierarchy is normal. That will be very interesting in the future for other problems. So as I said, the prior choice is something that you need to decide how to do. And this is an open problem that it is ongoing, but it's going to be very important when we start to collect the full sky and we say, okay, these are our data. We have all these different models. Which one do we want to choose? Beyond the parameter thing. Now, there is another thing that, just to finalize this introduction, that will be interesting, and then let me give you a quiz, since it is siesta time. All my talks are always during my siesta time, so I had to keep people awake, and myself especially. So imagine you wake up one day in the morning, you are making coffee, right? Like a good Italian, you all make coffee in the morning. And you find that there is just one single bean of coffee at the edge of the countertop, where the red arrow is. My question to you is, what is the rest of the coffee bag? Where?
Out there.
That's true, but where else could it be? Well, there are 2 answers. One is it is on the floor. It's just a spillover, right? So it was like a kind of random process. The other one is it is in the cabinet, and my daughter woke up in the morning and put it there. That's what you call a coincidence, right? Of course, you are used to these coincidences, right? Because there are total eclipses of the sun, and that's only because the moon is at the right distance to completely block the sun, right? I hope you agree that that's a coincidence, that nobody's working on a physical theory to explain that. Or, for example, why there is as much water as land on Earth. You know, the density, the height contrast on the surface of the Earth is only 1 kilometer. So a little bit more water and we should be covered. A little bit less and there should be dry land everywhere. That's the most common case. Now, this is what you call coincidences, and this is when you stop explaining things. So at what point do you decide that you are hitting the multiverse, and then you stop explaining things, that basically you are drawing things from a distribution? So for example, in the exoplanets case, that's the case, right? I mean, because there are so many exoplanets in the universe, in the galaxy, now we know that almost every star hosts an exoplanet. We just happen to be lucky. We just got the right lottery number. Now, when do you do that for the universe, when you are doing cosmology? So I do not know the answer to that. It's a complicated one, right? But we have been following an approach that we call actually model-independent cosmology, which is actually a way to extract features from the observations that are independent of the model used to infer those things, and therefore can help us to actually constrain the models of cosmology. And I will give you some examples about that from this list, that it is not exhaustive, but I will try to show you the most interesting stuff. Now, just to remind you, as a good observer of the sky, you can extract all the information, because these are random modes. This is a stochastic variable. So at some point, you are going to be limited by cosmic variance. So for example, the primary of the temperature of the CMB is done. Nobody has to do it ever again in the history of mankind. We can do the same with the galaxies. And I know here there's a huge effort on Euclid going on to try to see all the galaxies that you can get. But you could also think about just mapping all detectable galaxies by circa 2050 or so, right? And you see there how the surveys are growing exponentially. The important point is that, and I think it's a fair statement, this is not a technical problem, it's actually a money problem. If we had money, we could have already observed all the galaxies in the sky. So once you have them there, you can start to play with your data. So all the story that I have been telling you was very nice until maybe 10 years ago, 5 years ago, when there were no tensions. Right? So these tensions are these new things that you say, okay, what is happening is that when I analyze the CMB, I'm taking a screenshot at redshift 1000, I feed the model there, and then I extrapolate it. Locally, I can look at things like clustering, in this case sigma-8, or the expansion rate. And if the model is correct, it should predict exactly what I see. It doesn't, or at least it doesn't with some uncertainty, right? So this is the case of the fluctuations at 8 megaparsecs, that the green line from Planck is about 2 or 3 sigmas, this discordant with the clustering data from the quick lensing surveys. The most famous one is, of course, the Hubble tension, where the discrepancies of the order of 4 sigma or so. So you see here on the left column is measuring everything from the early universe. On the right column is measuring things from the local universe. And you see that the two data sets are not overlapping. Just walking down memory lane, I mean, we were the first one that actually quantified this tension almost 10 years ago, and actually predicted what should be the confidence levels of what is already happening. And it was already clear that something was going on there. But this is a fully Bayesian and rigorous way to actually quantify the tension. So there are two explanations. One is, of course, that the model is wrong, that this lambda CDM model that we have is wrong, and then we have to find a new model, and that's the most exciting explanation. The other one is that you have systematics, right, in the data, and then you have to explore the systematics. So here I'm going to give you a list, exhaustive, of how you check all the possible systematics. Now, the most difficult ones are the unknown unknowns. And you are Italian, so you understand ixus leones. Basically, whatever you don't know, you just say, okay, there were lions beyond the Levant, the Middle East. I don't know exactly what is happening there, right? Now, how you address that is very important here, because the answer is complementarity. Of course, having different probes and different data sets is the thing that is going to lead you to actually figure out if you have systematics or new physics. And I want to highlight here the review that I guess was accepted, led by Michele. This was a tremendous effort, really tremendous effort by Michele. But it is basically a review where he collected, and I want to give credit to Michele, all the alternative probes that you can have in the universe to actually check for these systematics. If all these pros are going to lead to give you attention, then at the end of the day, we are going to say, okay, this makes sense, and this is what we know about. One thing I want to emphasize is that this Hubble tension, if it is real, is an anchor problem. Because when you try to reconstruct expansion history in a model-independent way, or using splines, or if you want to be modern and you want to call machine learning Gaussian processes, same thing, is consistent with lambda CDM at the 1% level. So it is a mismatch of the anchors. So the new physics has to come either because the local universe is wrong or the early universe is wrong. That's something I want to emphasize. Don't try to look for solutions in the middle, because there's no wiggle room there to do that. So all you have been doing so far when you are looking at expansion history, or you are looking at the baryonic acoustic oscillations of the CMB, is looking into the surface of the pulse light cone, which I mark here, I denote here by red lines, right? Now, there is more interesting information elsewhere. You can try to devise methods to look inside the pulse light cone on the left here, or outside the pulse light cone, or actually, if you finally figure out all the systematics and everything, then you can predict the future, right? Because if you have the model correct, if lambda CDM was correct, then I can go all the way to the future, right? And that's what we like to do as physicists, right? To predict the future with accuracy. So I'm going to highlight here, but I'm not going to talk about, because Mikel is here, and I'm sure you heard a lot about that, about the cosmic chronometer method. This is what I want to emphasize is one thing. This is a fully cosmology model independent test. There's no cosmology here. The only thing I did there was to assume isotropy and homogeneity for any metric theory of gravity, which is extreme in general. And there, if you are able to measure how time changes, passes as a function of redshift, that's what is called a cosmic chronometer, then you can reconstruct the expansion history. Actually, you can do much more, and that's what I'm going to talk about. But one thing I want to highlight here is this plot from one of Michele's papers, which basically shows you the expansion rate divided by redshift as a function of redshift. And you see this transition between decelerating and accelerating universe. Now there was no cosmological input whatsoever. It's the first cosmology more independent confirmation that you live in a so-called of lambda cold dark matter universe. But I want to emphasize something more important than that. I put h of c in kilometers per second per megaparsecs for convenience for people to read it. But I could have put the stellar feature that was used, that was the 4,000 break, and completely forget about any models. Because the only thing you want to see is that there is a change in the slope. That would be completely model independent. I could have put here, I could have plotted here just the absorption feature in the spectrum and completely forget about any stellar models, and you will see that. I think those kind of cool things that have been done with this method are the thing that we want to see if we want to address that thing. There is enormous progress in this field. I'm sure that Michele has been upgrading you about that. One thing that I'm doing with Michele, actually, I'm even writing the Python code, so I'm doing with Michele. I'm going to just say, I'm not only talking about this. So it's, we are using something quite exciting on machine learning to actually get this age redshift relation with the photometry only. So more news on that will come very soon. Now, let me give you something that you have not heard about, and that goes well beyond what is usually done. One thing that you can try to do is to look inside the pulse light cone, which is impossible because that's not connected to us. It's casually disconnected. So how do you do that? Well, you just bring the information from the fossil record, because the galaxies, at some point, they were close to each other, and the pulse light cone was much smaller. So what we did there in that paper was to actually use something similar to the cosmic chronometer method to reconstruct the amount of homogeneity in the sky. Let me tell you one thing. The CMB is giving you isotropy, and the constraints are fantastic. It's 1 part in 10 to the 5. But homogeneity is something different. For that, you have to establish the insight of the past light cone. And that's what we did in that paper. And to my knowledge, is the only result so far that it is fully independent of the cosmological model that is constraining homogeneity at the 10% level. That chi-square curve there. I don't have time to go into the details. Also, I do not want to. The other thing that you can do is to look outside. Now, how do you look outside? It's again not causally connected. So the way you do it is actually you measure the curvature. So if there is a huge perturbation next to our horizon, this will be seen like a kind of curvature level. If there is if inflation lasted for thousands of epochs or millions of epochs, then the universe will be perfectly flat and it will go down. The curvature will go down to the cosmic variance level of 10 to the -5. So this is a very simple method. You basically have to combine. It's now gravitational waves are coming into play. You have to combine the cosmic chronometer methods or the cosmic clocks with the gravitational wave luminosity distance with high accuracy. So this is a very futuristic task, but we are theorists. We can write futuristic papers. You can actually measure that. So let me tell you a bit more about an extremely old subject and relevant to Bologna because people have been working a lot on globular clusters. So one thing you can do is to integrate the equation that I showed you before, and then you get H0 simply from measuring the age of the universe. So this is something that people have been doing since the 50s, actually. But something that people have not been doing is using all the information in the color magnitude diagram. Right? So it's usually the case that what you do is to just fit the main sequence luminosity turn off, and that's this point here. And then you try to estimate the age of these objects. But then you open up enormous degeneracies because that's degenerated with metallicity content, helium content, enhancement of alpha elements, and the distance, right? And then you have to get all this information from other sources to try to get it. With David Balsan did, as his PhD, and he's now a postdoc in Berkeley, is to actually use the whole morphology of the color magnitude diagram, because there, as you can see here in these plots, although most of the age information is in the main sequence turn-off, metallicity, alpha enhancement, and you can see more in the paper, have different shapes. So you are able to match and model the whole thing. You can actually get ages. The result is what you see down there on the right, where we establish what is the absolute age of the universe with those errors, statistical and systematic, using the full color magnitude diagram. Now, one thing I want to say is that, okay, thank you. Yeah, I'll finish in 5 minutes. Our method does estimate the distances by itself. We do not need any output. So we can compare with Gaian distances at posteriori. And that's what you see there as the one-to-one line. The distances from fitting the full color magnitude diagram agree remarkably well with the Gaia ones, which is quite a success. So now, let me just wrap up in 1 minute what the issue is. You can look at this problem that I showed you before, the expansion rate, in this diagram, just by looking at the sound horizon versus the Hubble constant. And then you see that if the CMB is giving you this, BO is crossing here, but the local universe is crossing here. Therefore, they are incompatible. And remember, in that equation, that's how you compute the sound horizon for the BAO. In that equation, everything is model dependent. Everything. CS, H, you have to assume what it is, right? So What we did was to actually incorporate here the results from the globular cluster ages. And that's what you see in this blue line. And you see that the blue line from the globular cluster ages prefers to be where the CMB is rather than where the local distance is. So at least as this independent probe is concerned, I would say that it likes to go in the direction of no tension. We'll see what happens, but I just wanted to show you the use of an independent probe. So let me just take you back to the 90s. I don't know if you remember, but in the 90s, we were playing with ages of globular clusters and galaxies. And well before the supernovas, we saw that there was a need for lambda. Nobody believed us. It was completely wrong. The reason being that, okay, stars are complicated objects. And who knows? Of course, we missed on the Nobel Prize, and then the other guys got it, although the universe was lambda. So here is the question for you. You miss on your physics because of your social beliefs and the theory of trusting, or you actually look in detail about what you are modeling and then check it out in detail. So I'm not going to talk about that, but just maybe 1 minute saying that you can actually do something really interesting, which is to constrain the Hubble parameter at recombination. If you analyze the CMB, removing the late time effects like lensing and integrated Sachs-Wolf, and what you get is something really remarkable, is that no matter what kind of energy density content you allow at redshift 1100, H is constrained to be 1% accuracy and in accordance to the lambda CDM1. So there's really no room if you want to put neutrinos, curvature at that redshift, what we call maturation, which is basically a equation of a state harder than 1/3, a dark energy fluid, nothing. It's like very, very lambda CDM-like. And in fact, if you want to do the ranking of models, the one from a Bayesian point of view, with the equation I started, you do see that the simple lambda CDM is much more favored than the other extensions from the data, with the corresponding priors that you can decide. So probably I was only 1 minute over time, so that's not too bad. Let me stop here. Let me tell you my conclusions. And my conclusions is that it's actually a very exciting time to be working in astronomical cosmology, because the big data are coming now. We have figured out the parameters, but that was almost like a children's play. Okay? The real challenge now is to understand the physics. What is the energy densities? What is the inflaton? What is the dark energy? What is going to happen to the new physics that we have there? What is the dark matter? I think there's an enormous opportunity now to figure out those things. And I hope the younger generations can help into that endeavor. Thank you.
The next talk. Time for questions from the public here and at home. Please raise your hand for the questions.
There's one.
Okay, go ahead.
I have a couple. So one, if you can go back to the.
Maybe it's easier for them to you.
One is to understand what is driving the better agreement between the globular cluster estimates with respect to the shoes sample you were mentioning.
It's a full independent probe, and it just came out to be that number. I don't know why that number is on the CMB rather than on the shoes. But basically, so the globular clusters are counting the universe from redshift 10 down to 0, weighted around somewhere between 1, and the rest, because it basically is an integrated quantity that counts everything between 10 and 0, and you have some weighted average there around redshift 1. But this is coming out like that. So this independent probe will favor not tension. You want me to say it in plain words.
Okay. And the other is maybe more fuzzy or philosophical. So in this view, which is now emerging all over the places, even in Hollywood, I guess, of the multiverse, etc. Yeah. If that's the mindset, why should it be important to constrain a cosmological parameter to the second digit if everything is
Random.
around? Yeah.
I agree with you. If that was the case, then we can stop tomorrow, because then everything will be the weather, right, or the angular size of the moon. But then it will be interesting to have proof that the multiverse exists, right? Because without proof, then it's a bit of random, like free thinking or empty thinking about these things. Let me give you a good example. I'm old enough that I remember the days when there were no exoplanets. The only planets we knew were theirs, right? And then everyone was saying, oh, look at this, we have Jupiter, we have the asteroid belt in the right place, we have the moon deflecting things, and then everyone said, this must be God, because everything is so fine-tuned in this place, right? And then suddenly you found out all these exoplanets. And now you say, oh, hello, I have proof now, right? There are so many of these systems that, it's not crazy that I'm just a coincidence. I'm just a lucky chance that I suffer from here. But in cosmology, you tell me, oh, I'm going to tell you that dark energy is just -1 because I'm lucky. I say, good, but where are the other tickets of the lottery? Right? Okay, you won, that's good, but where are the others? I think that would be my approach to this philosophical question. Okay. One thing I want to remark about the ages is that Michele also did something very nice with the cosmic chronometer, which is independent of this, and he used some Gaussian processes to actually extrapolate the measurements to predict what H naught should be, and you get something around 68. The error is still a bit big, so it's not decisive, what it should be, but that's also landing about that.
Question from Michele?
Yeah. When you talked about the prior and how fundamental they are, the question that I have is, at a certain point in our prior, we start to put in what we understand about physics. And this is a prior too.
Yes.
Because, for example, as you showed 20 years ago, omega lambda was 0,
and
this was a prior.
Right.
And everybody except a few were finding omega matter equal 1. So how to overcome this?
But as I said I think one has to be very, very, very careful, because it's exactly what you say. It's an unconscious bias. You have to be very careful about how you choose a bias. Exactly what you said. You either use like a well-known physics, like for example, we know what the symmetries are in our universe, in our standard model of physics. We know about what is going on, and then you use those rules as to decide your prior, or otherwise you are just basically constructing a prior based on your thoughts in your brain. I think it is a problem, and that's why I wanted to highlight it. It's a very serious problem. How are we going to choose the model? And here, the data will never overcome it. It's impossible. Look at the formula. I mean, it's not my word. Let's look at the formula. It's there. You integrate over all the plans. So, and just take a delta function of 1 over your model. That's it. It will always integrate to 1, no matter what the data are. Right? So it is a problem, but we should move to that level. Otherwise, I mean, parameter fitting is done already. We have done it. We know the parameters of this effective model.
More questions? Yes, please.
Assuming we have decisive measurement of the Hubble constant using the cosmic chronometers, and we get consistent measurement with the CMB, and want to explain this other measurement.
So the most straightforward explanation will be that there are systematics in there, right? I mean, this is precisely what I was trying to highlight here, that to check systematics, you need complementarity, right? So if you start to get other data sets, but for that, I would like to see something beyond the cosmic chronometer, other data sets that are coming together and telling you the same story, right? if everything is telling you the story that, and I think that's why Michele put together this review, if different probes are telling you the story that everything is consistent with the CMB and only the C phases stay by their own, there must be something there, right?
More questions from the public here? Nobody from home? Online participants, I don't see any question. So let's thank Raul again.
Thanks a lot.